back up a little bit. I want to turn now to this question of how do we count the infinite binary strings. We were talking about computable enumerability, and we also kind of had this maybe not more general concept of countability, the idea that you can, because it's hard to talk about being able to computably enumerate all of these binary strings, because if they're all infinite, then what does that mean to write them all down? You can't exactly write them all down, right? Can you? You can't exactly write one of them down. So it's a little weird to talk about the computable enumerability of like the set of all infinite binary strings. But you can think about the ability to kind of assign one as the first one, and one as the second one, right? And one as the third one. Maybe the third one's all zeros, right? Or, it goes on forever. Maybe this is the third one, and then, so forth. Is there a way to kind of count through all of them like this? Is there an assignment like this that works? Even if it's not computable, I mean, maybe it is, maybe it isn't. What would that even mean for it not to be computable? But in any case, this is what we were having trouble with, and I invited people to kind of think about how they might do it and come up empty, because you will. And in this video, among maybe other things, I'm not sure how we're going to get in this video, I want to prove that, here's a fact, this collection is not countable. You cannot do what I've been talking about here. You can't assign one of these infinite binary strings as a first guy, one of them as a second guy, one of them as a third guy, etc. And the proof of that is extremely, it really is, I mean, I do a lot of it. The proof is a very, it's a diagonalization argument is what it's called. So the proof is actually quite elegant and not that complicated. The way it works is this. We're going to go by way of contradiction. So here's the proof. This one I will prove, or at least show you why, and visually, maybe. I don't know how to, I don't know, yeah, you'll see. So suppose, by way of contradiction, that it was countable, that the set is countable. So suppose we could do this. Suppose we could assign something, so, i.e. we have a first infinite binary string, a second, a third, etc. ... Here's what we'll do. Do this. Do the following. Arrange them one below the other. Descending, i.e. descending. To make a table. So here's what we'll do. We'll make this table. So basically what I mean is that if we have a first thing, let's just list it. Maybe 1 0 1 1 0 1 1 0 1 1 ... Maybe that's my first infinite binary string in this count kind of ordering of the infinite binary strings that I supposedly have here, that I'm supposing I have one. And then maybe the other one is 1 0 1 1 0 1 1. I'm just going to write them all down. Maybe the next one's just all zeros. Maybe the next one's all ones. Who knows? So I'm just going to arrange them in descending order like this. Maybe one or two more. So like 0. Maybe we'll do alternating next. So suppose that there was some comprehensive ordering, and if there was, then I could make this table, right? If I could list them one at a time in a comprehensive way, then this would be a comprehensive kind of table, you could say. So what are we supposing here? So we are assuming that every single infinite binary string is one of the rows of this table, right? You ask for a binary string, it's got to be one of these, because that's the assumption. We're assuming we have all of them this way. So in particular, so here's what we do, and it's an immediate contradiction, and the reason why is that you can look at this diagonal I didn't draw it very well, but just like the 1-1 position, the 2-2 position, the 3-3 position, the 4-4 position, the 5-5 position. Take that infinite binary string. Now there's nothing really wrong with that, but if I took this diagonal and I inverted every single bit, if I turn this one into a 0 and this one into a 0 and this 0 into a 1 and this 1 into a 0 and this 0 into a 1 and I flipped all of them, then I would end up with an infinite binary string, and that has to be a row of this table. But that can't be a row of this table because I've purposefully made it disagree with at least one element of every single row. And that's the contradiction. So just assuming that I can arrange all of the infinite binary strings in this descending order like this, one at a time, and have all of them, that creates a logical fallacy. So let me put it this way. Take the take the diagonal elements and flip every bit to create an infinite bit string. And since we have all of them, it has to be somewhere on the table. So, maybe it's this. Maybe, say it's this guy right here. Well, if it's this guy right here, it's not. It can't be, because this 0 here, I purposefully flipped to a 1. This is going to be wrong. Fails. So, I mean, I flipped every, so, if I assume it's the fifth bit, if I assume it's the fifth row, then it can't be the fifth row because I flipped this 1 into a 0. And so at the fifth position, it's gonna disagree. So I basically created like a bit string that just can't exist anywhere on this table, and that's a contradiction because I was assuming that every bit string occurs on this table. It's a very simple argument. It's very elegant. It's a constructive argument. I get to create a bit string that just can't be part of my set. And so what's the contradiction? The contradiction is that I don't have one of these. If I'm assuming that I have a countable set of bit strings, it can't be all of them, because at least this one is missing. Maybe I'll write that down. So, if I assume I have a countable list of infinite bit strings, then I can always create a bit string that can't be on the list. Can't be in the list. And that's what I just did. Right? I assumed I had a countable infinite set of bit strings. I assumed that it was all of them, but that really isn't necessary, to prove my point. The point is that if I have any countable list of infinite bit strings, and then I can list them all this way, and then just from the structure of the list, I can always create another string just like these that just can't be on this list. That can't be one of these. That's diagonalization. You say that you've diagonalized out of the set, of the countable set. And this is an exploitable algorithm here. So, and I want to exploit it. But before we exploit it, let me kind of come to some conclusions here. So some conclusions that are important to kind of note. So conclusions. One is that uncountable sets exist. That's an interesting point on its own. Recall from the previous video that every decision problem is a bit string, is an infinite bit string. And also, every infinite bit string is a decision problem. In other words, the infinite bit strings are, the set of all infinite bit strings is the set of all decision problems. If you want to remember why that is, just watch the last video. But the idea is that if this is an infinite bit string, then it's also a decision problem because this second entry corresponds to the second string being a yes answer, right? The decision problem is a collection of strings such that the answer to the decision problem is yes, right? So what I'm saying here is I have some fixed enumeration of all strings in an alphabet, And I'm saying that the second string is a yes answer, the fourth string is a yes answer, the sixth string is a yes answer. So every infinite bit string is a decision problem. In fact, the set of decision problems is the set of infinite bit strings, i.e. the set of all decision problems, the set of all tasks that we might want a computer to solve for us, is, put that on call caps, is the set of all infinite bit strings. Therefore, I don't know if this is a 3, but therefore, the set of all decision problems is uncountable. So that's interesting because, remember, the set of all finite strings is countable. The set of all finite strings over an alphabet is countable. And because of that, we concluded that the set of all Turing machines is countable because when you write a program in a programming language, you write a finite string of text. And likewise, we can also design Turing machine. When we design a Turing machine, we can write it down on a piece of paper with a finite string of text. So the set of all Turing machines, is countable. It's in fact computably enumerable. We said that. We found a way. We essentially designed a Turing machine a couple of videos ago that could list out every Turing machine. And so the set of all Turing machines is countable. The set of all decision problems is uncountable. So we have a clear, very clear discrepancy here. On the one hand, the set of all Turing machines, and likewise by the Church-Turing thesis, the set of all tasks which are computable, the set of all tasks that are computable is countable. Meanwhile, the set of all tasks that you might want to solve is not countable. So to kind of put this together, the set of all computable tasks is countable, but the set of all tasks is not countable. So lots of things cannot be computable. Lots of decision problems cannot be computable. So there are lots of not computable things. So we have our first answer. We defined 3 complexity classes, or computability classes in the previous video. We defined R, remember, and Re, and All. So remember that this was all of the computable decision problems. Meanwhile, this was all the computably enumerable decision problems, and this was merely all the decision problems. So we still don't know about these two, but we certainly know now that regardless of either of these two, neither of them are equal to all. In fact, this is a much, much bigger set. This is an uncountable set, and these two are countable sets. So in a certain very kind of technical sense, and I don't want you to go too far with this reasoning, in a certain very technical sense, the vast, vast majority of problems are not computable. Lots of analogies can be made between uncountable and countable. You can say pretty hyperbolic things, like you throw a dart at a dartboard where all the real numbers are on a dartboard. The real numbers are also uncountable. The probability that you hit a rational number, a countable set, is 0. You could say stuff like that. But I don't want you to go too far with that, because remember that the decision to define decision problems the way we did, where any bit string corresponds to a decision problem, you should always consider the question of, like, how many of these random bit strings correspond to actual decision problems that I can say out loud in a concrete way, right? How many of these really matter in terms of how many of these bit strings correspond to decision problems that I actually care about? So, it's not, don't go too far with it. But we will have a better reason why these are, what we're going to do in the next video is we're going to exploit this idea and very naturally and easily create a problem that is not computable, like a specific problem. And not only will it be a specific problem that's not computable, but it will be a specific problem that I can state in words. It's a task that can be easily said out loud. And we will see that, and we will think about that.